the reason why a magnet pulls an iron bar. Magnetism and light are the earliest quantum phenomena that man came across because they're easy to access. Light is everywhere. Magnets, you find a magnet, there it is. And technology has been built around these things for a long time. I mean, the compass was invented by Chinese scholars in around 200 BC. So that means magnetism as a quantum phenomena has been known. The magnetism and the photon are the first quantum phenomenon known to human beings. One was obviously ignored until electricity came, but we'd like to know, why does a magnet pull an iron bar? This, I came across data collected back in 2001, and then everything was there. What is happening with an iron bar? It makes it, I should have looked at it more carefully back then, instead of looking for strange things. So what is alignment? When we talk about alignment, let's say this is a magnetic field. Purple is one pole, blue is... I'm demonstrating it like this because this is the conventional, from Maxwell, because from people interpreting Maxwell's second law, Gauss's law on magnetism. The interpretation could be wrong, but we are not here to deal with arguing about interpretations, but seeing why a magnet pulls iron. So this is our magnetic field. It's moving this way. See, so it's a blue field. I mean, they call it it has a dipole moment, and the magnetic wave moves like this. Then this is the electron, and it has a dipole moment. This is a vector, it's moving around like this, and so the electron will be like this in any position it likes, an unpaired electron. But once you put a magnetic field, they have to align. That's alignment. And note what alignment is. The magnetic field is moving that way. So when it reaches here, it will annihilate it. You understand? That's what alignment is. So first we have to understand what it is. Alignment. The iron bar literally becomes the opposite pole. It's magnetized in such a way that it literally emits the opposite pole, so that there can be a magnetic vacuum in between, So having understood what alignment is, we can now talk about what is affecting the attraction. So we have BA. We'll call BA the magnetic attraction. So it will be related positively to the magnetic field. And it will be related positively to the number of electrons per area that is a multiple of the Planck area at the surface. And we call this EU, electron unpaired. And then it will be inversely related to a function of distance, and it will be inversely related to the mass of the thing that it is pulling. That BA is the magnetic attraction. It's related positively to B, the magnetic field. It's related positively to EU, that is the Planck area a multiple of the Planck area, inversely related to a function of distance, we'll get to that, and inversely related to the mass of the thing. By using EU, we do not need magnetic permutation, the permeability of free space. That is it. Because the permeability, the magnetism, it's the electrons, the thing itself. So we can take that out and see where we go. That's it. That is the equation for it. But how does the magnet actually pull the ion? What is the process? Back in 2021, I collected data just to know, for curiosity's sake, the difference between north and south, what's happening there. And you'd find a line here. If the magnets are of equal is the thing, you'll find a line right down the middle where there's zero magnetic activity. It's all zero. You understand? So for F mid, we'll call it F mid, would be equal to the force of the north and the force of the south divided by 2, and it's equal at 0 here. Think of it as vectors. It will make it easier for you to understand why it's 0. You understand? But so even weighted, so FCL, this is the line of annihilation. CL is this line. It moves depending on the weight. So force weighted north plus force weighted south plus WN weighted north plus WS equals 0. But this can change. If south is stronger than north, this critical line will move this way. If north is stronger than south, the critical line will move this way. You understand? That's what's taking place. So now we can say this is the ion bar. It becomes the north. Because they are actually aligned. You understand? North and south are actually aligned. And south and iron will be aligned because the iron will become, and then this critical level though will be short. It will be around here. You understand? But Fi, the critical function, is a function of F EU over B. It could be north and south. But Fi over B, that means Fi, this attraction force, has to be greater than a certain critical level to pull this. And the critical level will be dependent on the electrons, on the mass, on the distance, and on the magnetic field itself. So that is what is happening. That's all what is happening. I wish I'd realized this back in 2021. So that's how a magnet pulls an ion bar. So it pulls an ion bar depending on the critical line. If the critical line is inside the ion, then it has low magnetic permeability. It's got to be outside, you understand? If it's inside the material, well, that's very low permeability, magnetic, you're not going to get it. It has to be outside, so that there's the vacuum outside and the pool. And we will talk about this pool in later videos, maybe. So at least now we understand. And we'll talk about the nature of the magnetism itself. Is it really that? I'm just doing this I'm not debating this only because I want you to understand how a magnet pulls an ion bar, and that's it. Like for magnetism has always been around, been used since 200 BC in technology. Why are we complicating it? I mean, because of the complications around me, it took me so long to figure it out, Anyway, thank you.